All right, so now let's calculate the specific heat of indium now that we know the specific heat of sapphire. So how are we going to do that? Oh, by the way, the source for the sapphire standard data is this one right here. The original primary literature is this Journal of Research of the National Bureau of Standards in 1982. And I actually got it from this application notes from TA Instruments. All right, so we've done that part. So now let's calculate the heat capacity. So heat capacity of indium divided by the heat capacity of the sapphire is just the ratio of the corrected DSC for indium to the corrected DSC of sapphire, okay? So, specific heat of indium times mass of indium, that's just the heat capacity of indium, right? And specific heat of sapphire times mass of sapphire is just the heat capacity of sapphire. So what's our formula for specific heat of indium? Let's see. Let's calculate first from here. We need heat capacity of indium, right? So you just multiply the right side by heat capacity of sapphire. So this is going to be DSC indium corrected divided by DSC sapphire corrected. Okay. Times heat capacity of sapphire, which we know. Actually, we don't. We know the specific heat of sapphire. So what should I do? I'm going to replace this by heat capacity of sapphire is what? Specific heat of sapphire times mass of sapphire, right? Do we have all the information we need?
Yep.
Okay, so that's how you get the specific heat of indium. All right, so let's do that. What's our formula? Wait a minute. That was just, we're not done yet with that one, huh?
That's not point.
That's just the heat capacity of indium. How do you get specific heat of indium?
Multiply it by the, no, divided by the.
Divide by the mass of indium.
Wait, that would plot that.
Yeah. Okay. So the ratio of the DSCs, indium over sapphire. So this is going to be equal to
10 over 10.
Okay. Equal to DSC of indium over sapphire. And then multiplied by
Fire specific heat.
specific heat of sapphire, which is this one, times the mass of the sapphire, which is 10.4 milligrams. Dollar sign that. And then
Divided by the mass of indium.
divided by the mass of indium.
Dollar.
Dollar sign. Okay. Let's check our units. Microwatts over microwatts. Cancel out. H10 is joules per Kelvin per gram.
And the milligrams cancel each other out.
And the milligram cancel each other out. So you get the right unit, joule per Kelvin per gram. 0.2634. You need a dollar sign on B3 and B4 because when you copy those, you want them to stay as B3 and B4.
I think the order of operations applies. Like, how does it know?
It's all multiplication and
It's all multiplication and division. It just goes left to right. Like in other words, the F10, H10, and B3 here, they're not all in the denominator.
Okay, so that's just. Oh, that's supposed to be sapphire, correct? You did Indium correct there. I know it's sort of.
Recording. So we have the specific heat of indium. Can we calculate the molar heat capacity of indium? How do you go from per gram to per mole?
Divided by the molar mass.
Per gram times grams per mole multiplied by the molar mass. So what's the molar mass of indium? Look it up. Let me clear this.
I mean, the
Molar mass of indium,
147.
114.818. So I would have the specific heat, joules per gram, times grams per mole, which is 114.818. That's 30.24, 30.4. So it ranges from 30 to about 33. You remember the law of Dulong empathy from the lecture?
A little bit.
Heat capacity, specific molar heat capacity of atomic solids are approximately equal to 3R. What is 3R? 3 times 8.314. It's about 25. So you can see it's close. Approximation. Okay. Question?
No,
All right. So that's the molar heat capacity. Let's compare that with the literature value. Let's see what the literature value is. Where's my handout? Let's look at the literature value. Specific heat of indium. About 0.23 joules per Kelvin per gram. Okay. So we're kind of off, huh?
No, well, a little bit. We got 0.26, 0.7.
Yeah. So anyway, that's the specific heat of indium. 0.26, yeah. All right. Let's calculate. The next thing we need to do is calculate delta H for heating indium from 60 to 150 degrees. What do we have to do? Isobaric heating at constant pressure. And so from 60 to 150 of Cp dt, right? That's your delta H. So we're just going to do sum of trapezoids, right? We're going to sum of your trapezoids of Cp delta T. The average Cp between for each trapezoid divided by times the delta T and then add them all up. Remember? So if this is your graph right here, you can say this trapezoid right here, the area of that would be the average Cp, the average of the Y values, right? So that would be the average of the Y values. And then multiply by delta T. This is delta T right here. And then add them all up. So let's go ahead and do that. So let's calculate the areas of our trapezoids. What did I do? So let's calculate the area of our first trapezoid. What would it be? The average Y value, Cp delta T, right? So this is equal to average Cp per mole. So this number plus this number times 0.5, that's the average, right? Times delta T, which is going to be 61 minus 60 here. That's the trapezoid. So that's 30.29. And then I'm just copy that down. And so my last trapezoid here is the average of these last two heat capacities times delta T. You got it? So now, how do I calculate delta H? From 50 to 150, from 60 to 150. Just add up all those trapezoids, right? So what do I use? What formula do I use to add up things? Sum equals sum of everything from here to down there. That is your delta H. Okay. How do you calculate delta S? Delta S is what? Integral of Cp dt over T from 60 to 150, right? dq over T. And that's equal to Cp d of dt over T is just d of ln T. Okay, so dt over T is just d of ln T. All right, so what we can do is, remember, if Cp was constant, that's just gonna be ln of T2 minus T1, right? That integral. So that's like Cp ln T2 minus ln T1. So this is your natural logs, right? I'm sorry. Oh, I'm sorry. I can't scroll because I'm writing on the smart, what do you call it? The tablet here. This is just gonna be Cp ln. If it was constant Cp, it's just gonna be Cp ln T2 over T1, right? So delta of ln T is just ln of T2 minus ln of T1. That's your delta X. So you, instead of integrating versus T, you integrate versus d ln of T. That's usually more convenient. So this is CPD of ln T. So from ln 60 to ln of 150, basically. So let's go ahead and do that. So our X is ln T, okay? So what would be our trapezoids here? It's gonna be CP, average of the CP, right? So it's gonna be this previous CP plus this next CP times 0.5, just like before. Okay, that's the average CP times delta ln of T. So ln, so pay attention to what I'm about to do here. I'm gonna do, let me move this away so it doesn't get in the way. Okay, let's do it again. It's going to be, what was it? Average of the CPs, right? So 0.5 times this CP plus this CP, correct? Times delta T. So parentheses, ln of T2 would be ln of 61, but it has to be in Kelvin. This is 61 degrees Celsius, so I have to add 273.15 to that one, minus ln of the temperature before, which is B10, right? But that's in Celsius, so I have to add 273.15 to that. So that's ln_T2 minus ln_T1, and then you have an extra closing parentheses. Okay, so if you hit enter, that's what you should get. So average of the CPs, ln of T2 in Kelvin minus ln of T1 in Kelvin. That's for that trapezoid right there. So that's actually the delta S for that interval. Okay. Next. What do you do next? Anything here that we need to dollar? No.
No.
So I just copy that. Okay, so that's your trapezoid. So if I add up all of those trapezoids, I get delta S, right?
Mhm.
So delta S is equal to the sum of these trapezoids here in column L. Close parenthesis. So the sum of L11 through L100, that's your delta S. And unit for that is joules per Kelvin per mole. Let's see if we assume the average, the CP is constant, and we'll just take the average CP. Let's see what delta H we're gonna get. Well, if we're gonna be doing let me approximation, you can say delta H, you can approximate delta H as average CP times delta T. Okay, CP delta T. Integral, it's like integrating CP delta dt. You just pull out your CP as a constant and treat that as the average. And so, what would that be? This is just going to be, how do I get the average of the CPs? Equals average of my CP, my molar heat capacities are these numbers right here. Average of J10 through 100 times delta T, which is 150 minus 60, right? 2848 versus 2848.19. Not too bad. Sorry, 2848.25. Is that why is that a good approximation? Well, look at your graph. Hasn't really changed much, has it? Which one's indium? Right there. Indium's more or less constant from 50 to 150 degrees. And that's why in a lot of our calculations, we can assume constant heat capacity versus temperature, because solids and liquids in particular, they more or less have constant heat capacities independent of temperature. Unless you're getting close to the melting point or getting close to the boiling point, you'll see a significant change. You're going to start to see significant changes in heat capacities. Okay? And we can do the same for entropy. You can do the average CP times LNT2 minus LNT1. This one right here. So what's our average CP here? Average of these CP values times, okay, close parenthesis, times. So this is going to be ln, how did I just do it? Times ln T2 over T1, or you can ln T2 minus T1. So ln parenthesis, okay, I have to put parenthesis first, and then ln of T2, which is 150 plus 273 plus 0.15, minus ln of T1, which is 60 plus 273.15, and then close parenthesis one more time. So that's the average CP times ln of T2 minus ln of T1 in Kelvin. And what are we getting? Pretty close number too. One right there. Okay. Recording.